Let me start by saying what I hope is the obvious. When adding vectors together, you have to add vectors that are of the same type. Let's just call it a rule that you can only add or subtract like vectors, i.e. velocity plus velocity is okay, but velocity plus acceleration, no. Okay, you can multiply vectors of different types together, just like numbers, but you can't add them together. They have to be of like type. We know that acceleration and velocity are related, but they're related through a set of rules. So you can't just add them together. Number two, you must agree on your frame of reference. Ahead of time. Also known as a coordinate system. Those are the things that I really want you to focus on here. So when we're adding vectors together, those are the rules. Or at least those are some considerations. I don't know if I want to say rules. So I'm going to produce what I feel is the simplest question I could possibly ask. You walk 35 meters at 30 degrees west of north. You take a break because you're weak. Then walk 50 meters at an angle of 50 degrees south of west. How far away are you from the start? And in what direction? But I'm not going to write anymore. I asked this question in fifth period and got blank stares, but do we all know that you can't possibly be 85 meters away? Are we sure?
Yeah.
Now, the truth is, these two vectors, your maximum displacement with these two vectors could be 85. Just like your minimum displacement between these two vectors would be 15. Direction means everything, right?
Yeah.
Because if I walked forward 35 and backwards 50, I'd be 15 meters away from where I started. But if I walked forwards 35 and forwards 50, I'd be 85 meters from where I started, right? But the angles make a difference. I mean, if I just blindly kind of drew some arrows, one of them is in the northwest area, and then another one is in the southwest area, and one's bigger than the other. Do you see why it can't possibly be the distance we thought? It's not going to be 85, right? It's going to be something less than 85, but something more than 15. All good? I want you to tell me how to do it. Or maybe I'll tell you how to do it. Now, there's probably one of you in here is going to tell me, yeah, just use the law of cosines. You probably could. The problem with the law of cosines is it's very incapable of telling you what direction you are from the start. It's only good at giving you the length. And I don't know what it is about the law of sines that you guys love so much, but you keep using it wrong. So let's stop, okay? Every time I see the law of sines on one of your papers, I know to check that sucker closely because you're just throwing stuff at the fan and seeing what spreads. So we're gonna assume for the time being that you'll do it my way until you can do it successfully on your own without me having to deal with it. So I will give you a set of steps. And the set of steps begins with, there are two vectors given here. The first one is 35 meters, and we use this kind of upside down division symbol to separate the magnitude of the vector from its direction. And it's directed 30 degrees west of north. That's the first vector. Then there's the second vector, which is 50 meters, directed 50 degrees south of west. So I see two vectors that have been given to us. I've identified all of the vectors given in the problem. Kind of take this and use it. It will become important that when you use a coordinate system, that you apply that coordinate system the same way to every vector. For example, I'm saying choose a coordinate system that makes sense. So here's a coordinate system. And I want to use one that makes sense, but it has to have certain features. So it looks like my problem is giving me my coordinates in reference to north, south, east, and west. We all know that these are the agreed upon arrangements, right? So you know this because I found one where they were not written like this, where south and west were flipped. That's not okay. It'd be okay to write north over here, but then east better be down there, right? That's not the important part. Although I do think you need to do that. That's not the important part. The important part is to go back through and determine, is north the positive direction or the negative direction? If I make north positive, I'm making south negative. And if I make east positive, I'm making west negative. That's important, because we can only deal with one-dimensional problems. This produces the directionality of our one-dimensional problems. So we will use this as our reference for all the problems we're going to do today, which will probably be just one. So I'm going to apply this to both. And save one for later. Now, some of you don't know how to read this, so I will read it to you as it should be read. 30 degrees west of north. So we're going to go to our next step. Now, 30 degrees west of north. I'm not going to write these little things down, but you should. 30 degrees west of north means to start at the north and turn towards the west 30 degrees. To understand how to get the angle in the right location, you start at the last direction, north. Turn in the direction of west. The amount that you turn is 30 degrees. Everybody understand how I did that?
Yes.
Start at the last direction, turn in the direction of the next direction, and then the angle is how much? So my next one. Start west, turn towards the south, 50 degrees. If you're not careful, you're clearly going to have the 30 or the 50 in the wrong place. And that messes up everything. Now, we're only going to work one of these at a time. So my next step is to break it into components. I believe you know how to do that, but I've been proven wrong. To break this into components, you need component vectors that lie along the north-south and east-west direction that can stand for the vector you've drawn. Now, what I used to tell students to try and make it easy is, they did not find it easy, is to wrap a triangle around the angle. Your triangle has to be aligned with your coordinate system. So one of them is going to be lined up with north-south, one of those is going to be lined up with east-west. This one is your east-west one. But I don't draw it there, I draw it up there. so that it makes a triangle. Is there clearly an implied triangle in this problem? Do you see it? Now that you see it, you should be able to figure out the size of those vectors. That's trig. That's you applying opposite, adjacent, hypotenuse. Do you need me for that? Do I need to step through that? I should not have to, but I have found that, tell you what I'll do. I will just talk out loud. I know that this is 35. It is the hypotenuse. And based on our naming convention, and I gave you rules about this a couple weeks ago, this is the opposite side and this is the adjacent side. I'm not going to write out all three trig functions. I am going to write out two of them because they matter. Sine 35 equal, sorry, not 35, sine of 30 equals opposite over 35. Cosine 30 equals adjacent over 35. And this is probably the last time you'll see me do all this kind of work. So if you have trouble with this, practice. So my opposite side is 17.5. My adjacent side looks to be 30.3. This is an intermediate step. You should keep lots of decimal places. I'm only going to write a few. Now, we are not quite done. We broke it up into components, meaning we found the size of the components, but now you should write a sentence that explains you understand what those are. For example, the opposite side is clearly in the negative x direction. So I will write that as negative 17.5 x hat. Negative 17.5 in the x direction. And then the adjacent side is clearly in the y direction, so 30.3 in the y direction. There's lots of ways to write vectors. This is just one of them. You can use imaginary numbers, you can use a rational number, you can use a lot of different things to write vectors. This is the way I've chosen to do it. This vector sentence is the same as this vector sentence. They say the same thing. All right, do the other one. I did it once, you do it once. So that should be what you get. The adjacent side is going to be 50 cosine 50. It should be made negative. And the opposite side is 50 sine 50. Now, when I look here, I've converted both my vectors to rectangular. I want to add the like components together. Add the y's together. Add the x's together. When I do that, well, it looks like the y's are going to be negative 8 in the y hat direction. And 17.5 plus 32.1 gives me 49.6 in the x hat direction, and it's negative. Technically, this is the answer. But it doesn't tell you how far away you are from the starting point. For that, you will probably need to do a little more work. So I would draw the components as 49.6 in the negative x direction, and then 8 in the negative y direction. These are components, they are at a right angle to each other. My result starts from the origin and is drawn to the end of the last vector. So 49.6 and 8. You should be able to figure out this and this. Now, expressing it in terms of north, south, east, and west, that might need a little more explanation tomorrow. identify, no, let me put a number 1 there, because you like me referring it to numbers. Number 1, identify all given vectors. Put it up there very long, but I don't care. Identify all given vectors. 2, determine, decide, agree. I don't know which word to use here. Probably the best word is apply a coordinate system to all vectors to be added. Now, I completely understand that this might seem like boring. This whole process to me bores me to death. But I want you to be cognizant that you are being, and our next step is to break each vector into its component vectors. Vocabulary word. Aligned with the coordinate system. Technically, we're going from polar to rectangular coordinates. That's what we're really doing. We're going from a polar projection to a rectangular projection. Next step, add like components, meaning components in the same direction. After you do that, you want to convert back to polar, meaning magnitude and direction. You're being shown things, and a lot of times you are victims of your own training. And although we talked a little bit about this in class, one of you came up to me and asked questions that still suggest that there's a problem here. Your math class would have you believe that this is where 0 is, and that the best way to go is this way for positive angles, producing 90 degrees here, or if you're really fancy, pi over 2. And it's not fancy at all, it's just different ways of measuring angles, and so on and so forth. Remember us talking about this just the other day?
Yes.
Look, the world doesn't always do that. North is 0, and east is 90. And that means that it goes this way on a compass. It's not wrong, it's just a different convention. I'm not going to give you your angles in 0 to 360 or 0 to 2 pi form. I'm going to give you your vectors relative to reasonable things that make sense in a problem. The ramp is inclined 30 degrees with the horizontal. The rope makes an angle of 75 degrees with the ceiling. Do you see what I'm saying? The ladder leaning against the wall makes an angle of 25 degrees at the wall. None of those are what your math class has taught you. Do you understand that? So, all the angles I'm going to give you are going to be between 0 and 90, with a point of relevance given in the problem. You will have to apply that uniformly. Now, you will have to, and this is where it becomes important that you